Hi, today we will talk about the AC-DC converters, or also known as rectifiers, and these things are used to convert the alternating current to direct current. And the usual schematic of these things are usually like that, where you have a block. You can have either single phase or three phase, and they are shown by a diode symbol here, and the input is AC, okay, and the output is DC. Of course, you can have like some filters like the capacitors and inductors, but we will omit those things in this course. But in the fourth year, if you choose power electronics area, there are two courses, 463 and 464 courses, which will cover those topologies in detail. Probably you have seen one of those in a circuit board or in a power supply. These are commercial single phase diode rectifiers, and they have like 4 pins. Two of them are for the AC input and two of them are for the DC output. They are also called bridge rectifiers, and they have that typical schematic like that. So they're also like half-wave rectifiers, so this is just an introduction. So probably you have seen these things in the circuit last year. So if you connect the diode to an AC supply with a resistive load, what will happen is the diode will get into the forward conduction and starts conducting whenever your AC is positive voltage. So it will, the output voltage, if I pull out the output voltage here, so the output voltage will be positive whenever AC is positive. However, when it gets into the negative voltage range, okay, whenever it's negative, the diode cannot conduct in the reverse direction, so it will block the current and the output voltage will be 0. So this is the half-wave rectifier, because we are only converting half of that thing and the other one that is 0. And of course you can connect the capacitor here and you can get a average voltage somewhere in the middle, and we will calculate it shortly. So this is half-wave rectifier, and this is again maybe the simplest rectifier, but it is not very efficient because we are not utilizing the half of the AC supply. So what we can do, and this is called full wave rectifier. So instead of just connecting one diode here, there are like 4 diodes. This is also called as like bridge rectifier because of like bridge shaped circuit. So whenever your input is positive, okay, so D1 will be in conduction and it will come back through D4, okay, whenever AC voltage is positive. However, when it is negative, when it is negative, it will flow through that path and it will come back like that. Okay, let me put the current directions. Okay, let me do with the other one as well. So here what you see is whenever it is positive we have the exact waveform, and whenever it is negative, basically we are inversing the output voltage. So whatever you do, the current direction, look at here, the current direction is always in the same direction. So we had a DC output. Okay, so here it is DC output. So if you look at the waveform, it looks like somewhere here. So this is our input. Okay, so whenever you put it to diode rectifier, it reverses the negative parts and you have that kind of output waveform. Again, you don't want that kind of DC output where it goes to 0 volts and goes to the peak, and usually the output voltage can be filtered connecting a capacitor or an L, but we will omit those things for now. So again, this is the output voltage, and this is more efficient than the half-wave rectifier because now the power transfer is also happening in the negative region as well. So the output is not staying at 0, but we have exactly the same output. So the question is, so again, this is the peak voltage. Okay, this is the peak voltage. The peak voltages are same, but how I can calculate the average output DC voltage? So average means So if I put a capacitor, I can get the highest ones and I can store some energy for the minimum values. So for the average voltage, okay, let's say I have an average voltage like that. So let's throw here. So this is V average DC, and the red area, okay, the red area under that average voltage will be equal to the blue area under those half sinusoids. So how can I calculate that average voltage so it will have the same area? In other words, if you take the average of that sinusoid, okay, let's say we have sine theta, okay, and if you would like to get 0 to, okay, this is P, 0 to P d theta, okay, and again this will give you the area, and if you divide it by 1 over P, that will give you the average voltage. Of course you can do it over 2P, it doesn't change anything because they are symmetrical. So the question is, what is the area under that sinusoid? Okay, so let's try to calculate that one, and actually let me try to throw a line at the horizontal here. Okay, so my first question is, let's forget the other average voltages, and let's say the peak value of that thing is 1. Okay, so if this is 1, okay, if this is 1, the peak value of that sinusoid is 1, what is the area under that 1 line? Again, it is not only important for power electronics, but you can use that knowledge in many engineering areas. So if this is 0, if this is high, okay, so the area under that one is equal to 2. And actually, again, it is really important to know by intuition, and you can use it in your engineering life. So let's calculate it properly. Let's calculate the area. So area is equal to 0 to P sine theta d theta, and the integral, the derivative of sine is cosine, and the integral is minus cosine, so minus cosine, okay, theta 0 to P, and you can write minus cosine P is minus 1 minus 1, okay, minus cosine 0 is again minus, there's another minus here, so it is minus 1, and that is equal to 2. Okay, so if that thing, the magnitude is 1, the area under that one sinusoid is 2. Very useful. Okay, so if I would like to calculate the average voltage, then that average voltage, okay, for peak value, if this is, let's say, average will be then that area divided by P. So that should be 2 over P. So if I have 2 over P here, the area, let me use the green one, okay, the area under the green rectangle will be equal to the area under that sinusoid if the average is 2 over P. Right, so again, I would like to calculate the average DC voltage. Again, you can take it not from 0 to P, but from 0 to 2P, and then you need to divide it by 2P. It just gives you the output voltage. But again, in our case, okay, this is the output voltage, and what is the output peak? It is square root 2 times V phase RMS. Okay, so if I have a phase voltage, the peak value will be square root 2 of that value. So instead of 1, I need to multiply it by 2P. Okay, so instead of 1 I have V phase RMS, and then the area under that one becomes 2. Okay, and actually if you would like to get 2 of those areas, it will be 4, so it can be either 2 times 2 divided by 2p. Okay, then that will cancel each other, so the output will be 2 square root 2 V phase RMS divided by P. Okay, so this is the output voltage, average output DC voltage of a full wave rectifier. And actually you can calculate it, and actually I want you to calculate with your calculators or mobile phones. 2 square root 2 divided by P is equal to 0.9, and actually you can have a look at the number of digits. It's really 0.900 something, so it is really accurate, and you can write 0.9 V phase RMS. Okay, so that is the average voltage of a single phase full bridge rectifier depending on your AC. So you can, you know, get slightly less value than your RMS voltage. So like common case, again, those rectifiers are used for grid connected applications and that kind of things. So if you have a 230 volts AC voltage, okay, the RMS is 230 volts, so DC voltage will be 207 volts. Okay, so that will be the output of a diode rectifier if you again, you know, filter it with our capacitors and that kind of thing. So you will convert to the average voltage, which will be 207 volts. So that is the single phase diode rectifier, so that will be again 207 volts if this is square root 230 volts. Okay, cool. So that is, you know, the voltage that you can play with. And once you convert it, again, I showed you some examples in the previous video. So for example, if you want to have a charger, so you can use a diode rectifier, and now you have 207 volts as DC with the filters and capacitors, and then you can use, for example, other DC converters, and you can convert it to 15 volts, 20 volts, I don't know, then you can have your DC output. Okay, so then we also have the three-phase full wave, you know, rectifiers or three-phase bridge rectifiers. So the connection is like that. I mean, at first it seems like strange, but if you just, you know, close that one and that one, okay, if you just close those lines, so that is exactly like the single phase rectifier. Okay, so you can use a single phase here, so it is like the single phase full bridge rectifier that we just discussed. So what we are doing is, these are all called legs. So instead of two legs, I have a third leg here. So the third leg is connected like that. Then I connect my first phase here, second phase to the second leg, and third phase to the third leg. Okay, so again, you know, how this thing works, you know, can be seem difficult, but actually it is not that complex. So what was happening in the single phase, okay, so you have either that connection path, one, or you have that connection path. So you had two possible configurations, and depending on those two possible configurations, you had either positive or negative voltage. So here, how many different possibilities that you have? For example, D1 can start conducting like that, and again it cannot go here, the current cannot go in that direction, so it has to flow through here, and again it cannot come back from D2, it will be a closed circuit. So the first one can go either from phase B or either can go from phase C, so VA, D1 or D4 or D6. Okay, so phase A can return either from phase B or phase C. So let's look at the other ones. So phase B, for example, that diode can start conducting and it cannot go that way. So again it is coming back, and now it can either go from phase C or it can go from phase C. So you see there basically two possible configurations for each phase, and there are like 3 phases, so there's like 6 different combinations. And for example, let's take one example. So for example, if I conduct from D1, okay, and if I return from here, I will show you the waveforms, don't worry for now, okay. So if it is coming all back from here, what I will see at the output voltage, output voltage for short amount of time, it will be VA directly connected to VC. So I will see VAC line to line voltage, okay, for blue one. Or let's see if, let's say that one is getting in the conduction, and I don't know, it is coming back through here, right? So let me put those things. So I will see VB here, okay, and VA at the negative. So V out for the other one will be VB, okay, because the positive one is connected to B and the negative one is connected to VA line to line voltage, right? So actually, if you think about it, there are like 6 different line to line combinations. So these are, it's not shown here, okay, so it's not here, let me write it here. So we have V line to line, we can have VAB, okay, we can have VBC, we can have VCA, like, you know, 120 degrees shifted of those voltages, and also I can have the negative values of those things. So VBA, you know, VCB and VAC. So there are like, you know, 6 possible output voltages. So whichever conducts, so how can you decide which one is going to connect, or how the diodes, you know, decide to get into conduction mode or not? So it was happening the same here. For example, here, if the voltage here is higher at the positive or negative, then the diode gets into the conduction. So the diode with the highest potential will block the other. So it will happen the same. So let me clean those things a little bit. So it will exactly happen. So if, for example, VA voltage is larger than VB voltage or VC voltage, then D1 will get into the conduction, and since that voltage is higher from that voltage, or that voltage is higher that voltage, it will block D1 and D3, so they will not get into the conduction, okay. So it will come here, then again the voltage here, you know, the potential, it is 0 for that one, so there will be no path for conduction. So again, now we have the same problem. If, for example, VB is more negative, it is, you know, the absolute value is larger in the negative value, then it will go back from VB, okay, because otherwise, so we have again 2 voltages here, we have the VB if it is here, and we have VC here. If VB is like having a larger magnitude, I mean they are negative, so having a highest amplitude here, so it will cause it to conduct here. So in other words, we have, you know, all those 6 possible output voltages, and the one with the highest voltage will conduct. Okay, so let me show that thing in the figure, so probably it will be easier to understand. So here I have just, you know, 3 line to line voltages. And actually I can draw 6 line to line voltages here. I mean, by 6 line to line voltages, let me show it here at first if you want. So for example, this one, okay, I don't know, let's give a label to that one. Okay, let's call that one VAB. Okay, and there's exactly negative of that one. Okay, so it looks like the single phase rectifier, and this is VBA. So they are like exactly negative to each other. Okay, and actually here what you see is, let me use the different colors. So for example, that one is the other phase. Okay, 120 degrees shifted. Let me use the orange. So that one is the other one. So we have the three phase or 3 line to line voltages, and plus the inverses of those things. Okay, so you don't have to worry about the waveforms, but at the end of the day, what I have, having a 6 line to line voltages, I have 6 line to line voltages. And now those waveforms are not 120 degrees apart, but they are all 60 degrees apart. Okay, so again, if you just look at the conduction, okay, so you have that kind of waveform. So let me go back and let me clean that part a little bit. Okay, so the output voltage, okay, the output voltage, throw that one. So you have all these possibilities, right? So 1, 2, 3, 4, 5, 6. So the one, let's say, is that one the higher, is that one the higher, that one, that one, that one. So for any time instant, there is like 1, 2, 3, 4, 5, 6 different voltages, and the combination with the highest output voltage, I mean, it is that one for now. So it is that one will get into the conduction. Now after that time, okay, so at that instant, it gets smaller and the other one gets larger. Okay, so then the output voltage will jump to that one, and it will jump to that one, then it will jump that one, right? So the output voltage will just follow the peak values of those things. Okay, that will be my output DC voltage, right? So again, it just keeps, again, if you just look at with the labels, first it will go VAB. So VAB means, let me go here, so let me clean that part a little bit. Okay, so VAB, for example, that one will get into the conduction, then it will come back through here in the first one, right? So let me write this one as blue, then it will jump to VAC. Okay, so VAC means, so it will still flowing through D1, but the return path is going to be changed to VAC, right? So then it will jump to VBC. Again, you don't have to worry about those combinations, just to show it. So VBC means now D1 will off because V phase becomes larger, then it will come back through here, right? But in any case, I will have a DC voltage. I will have a DC voltage and a current direction, constant current direction in those instances. And my output voltage, again, I think that figure is not correct because it will be slightly large. So then the problem is how we can calculate the output voltage. I mean, the idea is same. So I want to calculate an average voltage. So the area, okay, the area under that thing will be equal to area under all those curves. And actually you can represent those curves like that, right? They're like symmetrical areas, and actually in you have let me write 1, 2, 3, 4, 5, 6. Okay, so that all area, okay, or that thing will be 2p, and actually that thing will be 60 degrees, or p over 3. So each combination will be conducting for 60 degrees, and in total you will have a symmetry. What about that angle? Okay, so let's go for that one, for example 0. Let me draw it here for simplicity. So the area I would like to find is, I have that area where that is maximum, and let's say this is pi over 2, and this is pi, and I would like to find that area which is, you know, symmetrical. Okay, and that distance is 60 degrees, so pi over 3. And again, if this is, let's say, 90 degrees and I have 60 degrees here, so it is 90 plus 30 symmetrical, and 90 plus and 90 minus 30 degrees. So here it will be, you know, either 60 degrees and this is 120 degrees, or it is pi over 3 and this is 2 pi over 3. Alright, so I want to calculate that area, and if I can calculate that area, I can multiply it by 6 and I can divide by 2p, so I can calculate my average voltage, right? So let's try to write those things. Let me do it like in a separate slide. So let's say, let me draw it again. So the problem can be simplified as, so you have symmetry axis here, and you have pi over 3, you have 2 pi over 3 from 60 to 120 degrees, and I want to calculate that area, right? Let's do the same trick. Okay, let's say what happens if the magnitude is 1. Okay, so again, what is that area? Okay, the full sinusoid. Remember, the full sinusoid is 2. We do it before, and again that is another useful term. That area is 1. Okay, so actually all those areas, okay, so all those areas as like 0.5, so from 0 to 60 degrees it is 0.5. This is another 0.5 up to 90 degrees, another 0.5, another 0.5. So for example, if you have a cake having a sinusoidal shape, if you want to divide it 4, you need to divide at 60 degrees, 90 degrees, 120 degrees, and p. So let's calculate it mathematically, and let me write the equation. So it is sine theta, let's say from pi over 3 to 2 pi over 3 d theta. This is not the average voltage, this is the area. So let's try to calculate it, and again it is minus cosine, you know, theta pi over 3 to 2 pi over 3, and again for we cannot remember, so if this is 2 pi over 3, so that is minus 0.5, right? So the cosine is minus 0.5, so minus 0.5 minus 0.5, again you can write it, and that is equal to 1. Okay, and the average, okay, the average, let's say this is V average. Okay, V average for that one should be equal to 1 divided by P. So that rectangular equals having an area 1, and that red area also have an area equal to 1. So, and again let's go back, and we would like to calculate the average voltage. Okay, and for our example, the peak value, okay, the peak value is not equal to 1, but it is square root 2 V line to line voltage, V line to line RMS voltage. Okay, RMS. So here, instead of, let me draw it again. So I want to calculate that area, and the peak is square root 2 VLL RMS, and I will have, you know, that area, and I have 6 of those things. So V average DC is, I have in one of them, instead of area equal to 1, I will have square root 2 VLL RMS, and I have 6 of those areas, and I need to divide it by 2p, and actually you can write it like 3 square root 2 VLL RMS divided by p. Okay, and you can calculate that one. So 2 square root 2 divided p was 0.9, so that is 0.45 times 3, it is 1.35 times V line to line RMS. This is the output voltage of a 3-phase full bridge rectifier, right? So the output voltage is 3 square root 2 divided by P line to line RMS. Okay, again let's do the same thing. For if you have a normal grid, 230 volts like AC voltage, and the line to line voltage will be 400 volts RMS. So if you have a normal grid voltage, if you connect a 3-phase diode rectifier to that one, what you will get is, you know, 1.35 times 400 volts. This is 540 volts DC. So for example, I mean, that's a common voltage level. Let's say you want to drive a electric motor, AC electric motor, and in order to drive it you need to apply at different frequencies and that kind of thing. So what you do is, first you convert the grid voltage to DC, so you can have 540 volts DC, then you can invert it to whatever frequency that you need. So 540 volts is quite a common value in motor drives, in, you know, wind turbines, or in other you know, AC to DC, DC to AC, back to back converters. And again, that's all. There are like many details, like what happens if you connect a capacitor, inductor, what happens if the diodes are not ideal, you know, etc. So we will, if you choose the power electronics area, we will cover those things in the 4th year. And again, if there are any, if you are any curious about those things, and you can check those links. And actually the first 3 links are, I suggest them for everyone. So these are like online circuit simulation tools for diode rectifiers, so you can play with the parameters, and you can see the output waveforms. And if you would like to see what are the topics in the 463 course, you can check those slides. Okay, thank you.